Yoel Groman from the Hebrew University of Jerusalem, and he will speak about locality and deformations in relative symplectic cohomology. Please.
Okay. Thanks, Leonid. Thanks for inviting me. So the title of the talk is about locality and deformation in the relative symplectic cohomology. So what I will do is I will first kind of say what relative symplectic cohomology is as an object, and then I will discuss kind of like some methods of computation. So the basic setup is that we have a symplectic manifold M omega, which we assume is closed or geometrically bounded. And for kind of just to avoid all kinds of nuisances, I will assume that C1M, the first rank class, is 0. And in addition to the manifold, we're given a compact set K. Then to this setup is generally associated an invariant, which I denote by SH star sub M of K. And this is the symplectic cohomology of K relative to the manifold M. Now, before I describe what it is, I will describe what kind of object it is. So the kind of object is it has a number of structures. So first of all, it's a Z-graded module over the Novikov ring, where the Novikov ring is the set of formal sums, where you allow arbitrary positive, non-negative real powers, and you have some coefficients and some ground ring R, and you only require that these powers go to infinity. So that's the Novikov ring, and relative SH is a Z-graded module over it. In addition, it carries a non-Archimedean norm. So you can say, given an element, you can associate a real number, which says what is the size. And we have some completeness with respect to this norm. And finally, there are some algebraic structures. Namely, there's a product, a pair of fence product, and it has a BV operator. So it's a BV algebra with respect to these structures. And then maybe the most important thing is if you have a pair of nested inclusions, so if you have K1 inside K2, then you get a restriction map which goes in the opposite direction, and it's functorial when you have more nested inclusions, and it preserves all the structures. And maybe I should also say, and it's norm non-increasing. Okay, these are the structures. And then if you want a formal definition, well, so at least as a module, so in favorable cases, at least, you can consider the following thing. So you consider HK to be the set of all functions, which are like time-dependent functions, which are less than 0 on K. And then in favorable cases, you can just write down a formula for the homology where you take a direct limit over H, where H is over these functions, and you so I assume everybody knows what is truncated Floer homology, but now you're taking a limit over all functions which satisfy this condition. And then you take the inverse limit over all truncations. And when you say limit, you have to say what are the maps. So the maps are kind of induced by monotone homotopies. So given a pair of Hamiltonians, you can connect them by a monotone homotopy. So you're taking a limit over this kind of directed system. So in favorable cases, this is all there is to it. In general, the part where you take this inverse limit has to be in some sense derived, but that will not matter at all for our discussions today. So maybe it's easier to think of this as just Floer homology of the characteristic function of M minus k. That's another way one can make precise sense of this. But okay, so this is all just formulations. So are there any questions so far?
Yes, probably. So characteristic function of m minus k equal to 1 on the complement.
K means infinity. No, like there's the indicator when this means, yeah, that, at least the convention that I like, meaning that like this function here is infinity.
Okay, good.
On m minus k and 0 on k. So that's the okay. So that's the basic setup, and then the first question. Yes.
Norm is induced by the subnorm, like when you take the orbits as basis.
Yes, yes. The norm is kind of like whenever you have an you have kind of an action. Basically, it's kind of in this formulation. It's there because basically you have every element here. So kind of generators, you assign the norm 1, and then you allow combinations. So they have a certain norm given coming from the Novikov ring, and as you said, it's the sup norm. Okay. So the question is, of course, is this invariant ever computable? And in general, of course, this is quite hopeless. And why is it hopeless? So we have two different reasons. Like one is that the Floer complex is defined using closed orbits of Hamilton's equation, and we can't solve that equation. And even if we did know how to solve that equation, then we have a problem that we don't know how to solve Floer's equation. But I want to emphasize that these problems are not exactly on the same footing, because Hamilton's equation is kind of, it's a geometric thing. It's given to us by geometry. But whereas Floer's equation, we are free to play around with it. So in some sense, if we know how to deal with Hamilton's equation, the part about Floer's equation is more of a topological problem. At least one hopes. And that's so in fact, that's the subject of the talk, is that if you consider the case of integrable systems, then this problem of computability becomes a lot more tractable. So we want to consider the situation of integrable systems. So we're considering. So we have our symplectic manifold that we fixed before. So it's of dimension 2n, and it carries a proper surjection onto some smooth n-dimensional manifold, and we assume some kind of commutativity of like functions which are pulled back from the base, like any two functions which are pulled back from the base of this surjection, Poisson commute. And some other way of saying this is that the generic fiber here is a Lagrangian torus. Okay, so that's kind of a setup. And then what are the compact sets? So the compact sets means we look at some P, a subset of the base, and we want to study the symplectic homology of this pre-image relative to some ambient manifold. Okay, that's the setup. That's the kind of, so throughout we will be talking about this. This kind of will keep referring to pi, m, b, and maybe to p. So, yeah. So are there any questions? Okay. So as a little bit of motivation, I will mention a result by Varolgunes, which says that in this kind of setup where you have this cover of M by subsets such as these, which are pulled back from the base of a Lagrangian torus fibration, then there is some kind of Meyer torus property which relates a global Floer theoretic invariant, say quantum cohomology, with these invariants which you associate to elements of such a cover. And I should say this is only true for covers like this, the one we are considering. For example, if you consider a cover a symplectic manifold by balls, by kind of balls which are like topological balls or symplectic balls. So if the balls are small enough that they're displaceable, and the relative symplectic homology of the displaceable set is 0. So in general, you can't. It's not reasonable that you should be able to piece together global invariants from things which are locally 0. So the appropriate notion, like if you think in topology, the way to study topologies is kind of decompose something, decompose a global problem into local pieces. So it looks like the appropriate way to do this in symplectic geometry is to decompose by some kind of Lagrangian torus fibration. Yeah. So that makes this problem hopefully not seem so too specialized. I think it's kind of a general strategy for studying Floer theory. Okay, so that's the motivation, and I've presented the problem. So let's first discuss a basic case. So the basic case is where you consider kind of the mother of all integrable systems. You have you consider the cotangent bundle of the n torus, and so that's M, and the base is the fiber, which is canonically the real number, the kind of Rn Euclidean space, and the projection is just forgetting the position and remembering only the momentum. So that's the setup, and then we consider a convex polytope inside Rn with rational slopes. And that's kind of the one case of where Floer theory is very easy to compute. And I'll give you the answer. I'll describe the answer over the Novikov field. Over the Novikov ring, so the difference between Novikov field and Novikov ring is that we invert T. We allow kind of the Novikov parameter to be inverted. So over the Novikov field, the answer is given here by a formula. So what's written here is basically in degree 0 you have the Laurent polynomials with coefficients in the Novikov ring, and in degree 1 you have all these vector fields, and then in the higher degrees are just kind of polyvector fields. But then there's also a completion, and completion means with respect to a norm, because this thing, what I described here, is independent of any, doesn't take into account the norm, but the norm comes in here, and the description of the norm is, I tell you what is the norm of any monomial, and then what is the norm of these things. So the norm of a monomial. So a monomial has this multi-index I, and so this I corresponds to some integral, some function on Rn, and then so some vector, and then we look at the kind of the level sets, and since we're considering a convex polytope, there's some particular point where this level set touches the map, like the last time it touches this region, and then we have a position vector, and we take the inner product with a position vector, and this position vector is with respect to some point chosen arbitrarily. It doesn't affect the answer. So this is the norm. So a better way of thinking about the norm is well, you should think of it in the following way. You should think of each, so when you have a polygon like this, it also defines some domain inside a certain rigid analytic manifold, rigid analytic variety, which is just take the Novikov ring minus the origin and take it to the power of n. So this is kind of a formal torus, and then you consider the set of points whose valuation lies in this polygon, and then then this thing is just taking the soup norm. Like each such monomial defines a function, and this is just taking the soup norm with respect to this domain. So you should think of this as kind of this thing gives us the mirror dual to the symplectic region. Okay. Okay, so this is more or less a full description of, I mean, this describes also the product. Maybe I didn't describe the BV, but the BV operator, it's like the BV operator can also be described. It's kind of dual to the exterior derivative. Like you have some kind of, you can describe, you have this kind of Calabi-Yau form, omega, and you can apply it to vectors in the standard way. So dzi is dual to partial zi, and then under this duality, the BV operator maps to the exterior derivative. So that's kind of a full answer of what is relative symplectic cohomology in the simplest possible case.
And when you say that the norm is independent of your reference point, you mean that a different choice gives you something isomorphic, something?
Yes, yes. Different choice would kind of correspond to, like a different choice is like changing coordinates. Yeah. So it would amount to like if you think of this as like C star squared, as C star to the n, then a different choice is like acting by the action of C star. So it's some change of coordinates. Yeah. And that's over the Novikov field. If you work over the Novikov ring, maybe there's some, it's a different story.
Wait, so here you take the field?
What?
Here you take, when you write lambda nov, here you mean the field?
Yeah. I'm allowing T to be inverted. If not, then you have to be more careful about how you describe the product, and you have to be so they have to put in all kinds of coefficients. So I prefer not to do that.
But in theory you could, or not necessarily.
Yeah. There's a way to write this down over the Novikov ring, and the answer is a little more involved. But okay, so that's the simplest case. Now we want to consider the general case. So general case means we have some manifold which is closed or geometrically bounded, and then our pi, we allow it to have all kinds of singular fibers. So we want to say, what can we say about relative SH in such a case? So first, let's focus on the case where we start out with some subset which is contained in the regular part. So B-reg is my notation for a set of regular values. And we focus on such a thing, and then we have then we have this pi to the -1 of p is some open symplectic manifold, and it has two different embeddings: one into the cotangent bundle of the torus, and one into the cotangent bundle. And one into this symplectic manifold M that we are given, and we we want to know, is there any relation between these two invariants? In other words, what is the dependence of the symplectic homology of a domain on its ambient space?
Sorry, you assume that there exists a map from pi inverse of p to t star Tn. It's extra assumption.
Yes, I guess, because yeah, of course. So I mean, I wrote that it's contained in the regular part, but that alone is not enough. It's a regular part, and let's say, even for the sake, let's even assume that it's a convex polytope.
Okay, thank you.
Integral affine polytope. So yeah, it's an assumption that's kind of, but of course, it's kind of something which is intrinsic. Like once you are given P, you can kind of see whether it has this embedding. Okay, so I want to discuss two locality results. So one is already on the archive. So it's a result which I have joined with Umut Varolgunes, which concerns the case of complete embeddings, and the other is a result which is still in preparation about a certain locality spectral sequence. So let me discuss these results. So first, what is a complete embedding? So a complete embedding means that the following thing. So you have a symplectic embedding of a symplectic manifold Y into a symplectic manifold X, where your assumption is that X and Y are geometrically bounded. And it maybe makes sense to recall what is the definition of geometrically bounded. So it means that each of them carries a complete compatible metric. So compatible here means induced by kind of a compatible almost complex structure. And we require that this metric satisfies a bound on the curvature from above and a bound on the radius of injectivity from below. And of course, it's very important that we say the word complete, because if it's not complete, then many things, then anything is like anything. Okay, I don't want to say it, but it would be quite easy to satisfy these conditions without completeness. So the word complete embedding refers to the case where kind of both the ambient space and the included space are geometrically bounded. So let's see examples. So an example of something like this is if you start with the cylinder and you remove a ray. So let me just draw a picture. So you just remove a ray. Then you can see that the inclusion of this is basically it's symplectomorphic to the cylinder. Like the inclusion of the complement of the ray into the cylinder is itself symplectomorphic to a cylinder. So it satisfies our definition. Similarly, if you have kind of an open inclusion of smooth manifolds, then you take the cotangent bundle of one into the other, then one can show that each one separately can be endowed with a geometrically bounded metric. Note, like this example is meant to show that you can't take a geometrically bounded manifold on the ambient space and restrict it to the included space and get something which is geometrically bounded, because such a thing would not be complete. The point, like the completeness condition here is just, or the geometric boundedness condition only says there exists some other almost complex structure which is not induced from the ambient space, such that you have this kind of completeness. So I've given you, yes. Is there a question?
Yeah, so I'm confused actually. So one again, so did you define complete embedding already?
Yes. This is the definition.
Repeat.
Yeah.
So just embedding one manifold to another, and they're separately geometrically bound.
Yeah.
And
That's
no relation between metrics.
No relation between, except that both are compatible with respect to a symplectic form, which is.
Of course.
And non-examples are, well, if you take the ball inside the C, then the ball does not carry a complete, doesn't carry any, like a complete metric you can't find, which will satisfy this. Similarly, C star, the inclusion of C star into C. So these two things are easy to prove. But for example, something which I think is a lot harder is if you take C star times C. And you want to prove that it doesn't carry a geometrically bounded almost complex structure. That's kind of, I think it's hard symplectic topology. It's kind of like Groves not squeezing. So maybe you're wondering why like this terminology is a little weird, but the point is that complete kind of distinguishes like completeness here kind of refers to, like sometimes you have an embedding of a part of a symplectic manifold, and geometrically bounded means that you have the entire symplectic manifold. So complete means that it's not just some part, but the entire thing. I hope, yeah, that's terminology. Okay, so that's the setup, and then in this setup we consider the following case. So suppose we have a compact set K, which fits into. So K here is compact. So which fits into a diagram like this, where the inclusion of Y into X is a complete embedding. Then in that case, we have the theorem by Varolgunes and myself is that there is a canonical isomorphism between the symplectic cohomology of the relative to the included domain and the relative symplectic cohomology of the ambient, the included space and the ambient space. Okay. So an example where this kind of so how this is used, which is relevant to kind of so now I've kind of formulated something which is about geometrically bounded manifolds, but I want to say something which is specific to integrable systems. So there's some kind of class of examples which are called symplectic cluster manifolds. So the situation is, well, what is a symplectic cluster manifold? So the setup is as follows. So we have some 4-dimensional symplectic manifold M, and then our base manifold, we assume that it's diffeomorphic to R2. And we have our torus fibration pi, and pi has a number of properties. So first we require that there is kind of a finite number of critical points, and we require that all the singularities are nodal, or maybe it's more familiar as singularities of focus type. And so that's so we have this kind of nodal fibration, and then we have some kind of assumption on what the kind of induced integral affine structure is. It's a little more complicated to state this assumption. So the assumption is as follows. So for each critical point, P, we can find a Lagrangian tail, LP. So a Lagrangian tail just means a Lagrangian disk, as in this picture, which emanates from the critical point. And we require that this thing is properly embedded. And we require that we make a choice for each of the singularities, so that they are pairwise disjoint. So you consider like a 4-dimensional manifold with the Lagrangian torus fibration, finite number of critical points, and from each one there emanates some properly embedded Lagrangian disk, and they're pairwise disjoint. Okay, and then I'm not finished with kind of formulating the kind of what the assumption. So that thing induces some kind of integral affine structure on R2, and since you have singularities, this is not the standard integral affine structure, because when you go around a singular value, you get you have some monodromy, which I'm not describing here, and now the assumption about Lagrangian tails says that you have if you think about it a little bit, each Lagrangian tail projects some ray. So we have this collection of rays in R2, and we're making some kind of completeness assumption about this integral affine structure, which is that if we have rays, if we start with a point with a point anywhere, and we go in any direction, then as long as we don't hit any of these rays, we can still continue it. So we don't fall off the universe. So this is some kind of completeness assumption about this integral affine structure. So I see there's a question. So yes, so Shira is asking if I assume that LP doesn't limit to any other critical point other than P. Yeah, so that I'm assuming. So anyhow, so we have this. So this is kind of a description of some symplectic manifold with the torus fibration, and the theorem that we've proven is that if you take the symplectic manifold and then you remove all these Lagrangian disks, what is left is a copy of T star T2. So not some like this is as a symplectic statement, not some topological statement. Okay, and then so this is kind of a non-trivial example of this phenomenon of complete embeddings, and which is kind of relevant. And so let me say a few words about this. So so this data, so if we have a fixed manifold M, then we have some additional data of this Lagrangian torus fibration and the collection of Lagrangian tails. So we call this data a cluster presentation for M. But a given M can have many different such presentations. Now, so if, in particular, if we have some K, some compact or some polygon, then that polygon will be contained in many different copies of T star T2. So for example, if we look at this picture and we look at the polygon over here, then there's a copy of T star T2 which corresponds to these three rays. But one thing you can always do is take the ray in the reverse direction, and that will give you a completely different copy of T star T2. Thus you will get kind of two different maps. So if you look, so our locality isomorphism gives you a map from a symplectic homology relative to M to T star T2. So one map is associated with having the ray going off in this direction, but then there's another map with having the ray going off in this direction. So this gives you some kind of non-trivial automorphism of the symplectic cohomology of T star T2 with itself. Okay. Is this point understood?
And may I ask you, so what happened with singular fibers under this identification?
I removed them because I removed the Lagrange. Like how does this isomorphism, I'm saying once you remove them, so you remove the singular points, then this becomes, so it's not like this symplectomorphism is not compatible with not entirely compatible with the fibration. So if you want to have a model for this, let's go back to like a simple model for.
I thought that LP are this Lagrangians which grow over the rays, but you also have singular fibers, right?
Yes.
So you don't.
I just remove. So if you were considering a one-dimensional model, so this picture, so this is like you remove this you just remove a ray, and then what happens is here you have like complete fibers, and here if you insist on keeping the original fibration, then they become just half lines. But you can modify the fibration in a small neighborhood, like so you get fibers like this. Mm-hmm. So that's what like to construct this symplectomorphism, you modify the fibration around each Lagrangian disk. Mm-hmm. Okay. And so after you remove these disks, it becomes symplectomorphic. So there are no singularities, and it becomes symplectomorphic to T star T2.
Thank you.
So yeah. So it must be said that kind of you can, the fibration definitely gets modified in a small neighborhood of each ray. You can't, but you can make this kind of, you can make the modification be supported in a small neighborhood of the ray as you want. Okay. So anyhow, so this thing, some work in progress. Where one can actually work out what this automorphism that I was describing looks like, and it's something called a cluster transformation. But like going into details is a subject for another talk. But all I want to say is kind of that you can, like, well, you might think that since like a locality result, it says that the picture looks like the local picture. Then it would kind of say that there's nothing interesting going on. But the point is that there is something interesting going on because when you look in the neighborhood of a singularity, you have these different identifications. So that makes it so there's something. So the source of like why something interesting is going on is in this automorphism, and that's a non-trivial thing which doesn't exist, for example, when you have no singularities. Okay, so that's kind of one type of locality result, which involves complete embeddings. Now, I want to also say something about a different type of locality result. So this locality result, it's kind of, well, it has like two limitations. One is that if you have a closed manifold, then you don't have any complete embeddings, because by definition, a complete embedding, like a geometrically bounded symplectic manifold, always has infinite volume. And something which maybe I don't have so well how to explain right now is that if you want to study a relative SH for neighborhoods of singular fibers, you need more than just to understand the case of complete embeddings. And one thing to say is that, well, you need, so this concept of complete embeddings assumes that you have something that you already know, and then you want to transport it into some other situation. But say if you want to study the relative SH of a neighborhood of a singularity, then you don't have something to start. Like even the case where you just have this one singularity and it's completely local, there's still a lot of work to kind of understand what is the relative SH of the neighborhood of the singularity, rather than something contained in the complement of the neighborhood. So I want to discuss a little bit a different kind of idea, which kind of applies specifically in the case of when the thing you're embedding is a Liouville domain. So far we were just talking about you have a pair of geometrically bounded symplectic manifolds, and that was it. You didn't need any more than that because you had a complete embedding. But now we're going to talk about cases where what the embedded space is not complete. You don't have a complete embedding. You have some domain D, but you are assuming that it's a Liouville domain, and we want to kind of compare symplectic cohomology of some Liouville domain inside some manifold with symplectic cohomology of D relative to its completion D bar. That's the kind of thing we want to study. So suppose we have this Liouville domain, and suppose we have this embedding of the Liouville domain into M. So the Liouville domain comes with a Liouville form, such that the symplectic form it should be restricted to I guess to the image of D is the differential of the or no, maybe I should say I star omega D. I star omega equals theta. Okay, so that's the we have this this assumption, and then such a setup where you have a global symplectic form, and the symplectic form is not assumed to be exact, and locally in some open set you have a primitive that gives rise to a relative class, in a relative homology class. Namely, if you have something whose boundary you have a two class with boundary on this domain, then you can subtract this one form, and using Stokes' theorem, you see that this defines this gives rise to a well-defined class. Okay, so you have this. So this relative class is part of comes with the data, and then you want to study the Floer theory of the domain relative to the ambient space M. Then you have two types of Floer trajectories. You have Floer trajectories which go inside, which connect, like at least when you consider, like you should consider some Hamiltonians which have real dynamics occurring near the boundary, and then for two such things, if you have a Floer trajectory connecting, so if you have something in kind of D relative to D bar, then any such trajectory will also exist in M. But then you will have additional Floer trajectories which go around in M and they go outside. And I should say that I'm kind of glossing over something. It's a certain technical point, in that the Hamiltonians that I use to compute D relative to D bar are outside of M. They have different dynamics than the Hamiltonians that I use to compute D relative to M, because here it's a compact manifold, so at least we'll have some critical points. So there must be, and I'm kind of glossing over that. I'm kind of pretending that as far as the kind of the input of kind of the Hamiltonian dynamics input only comes from the boundary and the inside, and the effect of kind of the ambient space is that it allows Floer trajectories which go around the manifold. This has to be made precise, and this is kind of I have a work in progress which gives a rigorous formulation of what I just said. But for now, let's just pretend that this is this is a convenient picture and basically correct. So now the integrated maximum principle tells us that Floer trajectories, which like Floer trajectories which go outside, we can integrate this relative class on them, and so the integrated maximum says that this thing is always greater than 0. And in fact, one can show that it's greater than some positive constant. So if you have something which goes outside, then this class will be positive by some definite amount. So are there any questions?
Yes. How do you show that it's greater than some positive amount?
The fact that it's greater than some positive amount is some monotonicity. So because outside this looks very much like you can set it up so that everything looks very close to constant. So outside, so the fact that it goes outside, it has to intersect some divisor. It has to go pretty far outside, so you can use that to extract some positive constant.
And it will depend on the embedding of D into M.
It will depend on the embedding of D into M, yes. In a weak, yes, but in kind of a weak way. Yeah, it will. Let me just. Yeah, it will depend on the embedding of D into M, definitely. Okay, so this allows us to this defines a filtration. So I mean, you can filter. So this is the natural setup where you think of one thing as a deformation of the other. And such a thing gives rise formally to a spectral sequence. And the spectral sequence will have its first page that will be the symplectic cohomology with coefficients in whatever the ground ring is. And this thing will weakly converge. This is kind of a weak convergence to the thing we care about. Okay? Now this is a general statement. It's not like there's some work in making it rigorous, but still it's kind of not a very strong statement. Okay, so you have this spectral sequence, and let me refer to it as the locality spectral sequence. Now the big problem with it is that it doesn't necessarily converge. So and we can see exactly like we can see an example that it doesn't converge, and that example also shows us what is the problem. Why does it not converge? So the basic example is you consider you have your manifold is a sphere of area 1, and then you take a disk of area R, which is, I think it should be strictly greater than 2. Well, the first page in the spectral sequence is necessarily 0 because we know that the symplectic homology of the disk is 0. And notice the symplectic homology here, this is kind of a symplectic homology which doesn't take into account any torsion. This is the this is 0. On the other hand, we know that the symplectic homology of a disk of area greater than 2. So if it's kind of as in here, a disk which greater than 1/2. So we have something whose complement is displaceable, then it's known that this equals the quantum cohomology. So obviously there cannot be, the spectral sequence doesn't converge. Now, but if we look at this a little more carefully, we can see why the spectral sequence doesn't converge. And we can understand what is the complex. And the chain complex is
I'm sorry. I guess you meant the sphere has area 2 and the disk has area 1?
The sphere has area. Yeah, but it was kind of.
I guess,
said
I guess if you embed the disk in the sphere.
Yeah. No. It had initially it had 1/2.
Or 1/2. Okay, that also works. Okay.
Yeah. I fixed the greater than equal to greater, but then I must have also changed something else, I think. But anyhow, yes. But definitely. So one can write down what is the complex, and so what happens is you have kind of like what are the like if you compute what are the Reeb orbits of a disk, then you have a critical point, which is here, and then you have Reeb orbits, and each one goes around any number of times. So you have one which goes around once, and then one which goes around twice. I guess I should have numbered them 0, 1, 2, 3, but let's ignore that. And each like a critical point gives you just one generator, while a Reeb orbit is an S1 family. So it kind of it gives you 2 generators, one which is in degree in odd degree, and one which is in even degree. Now if you compute the differential, then so the red part represents the deformation. So if you do before the deformation, where you only look at Floer trajectories which go inside, then these are the Floer trajectories that you have, and they are weighted by something which is the area of the disk. But if you add but now that you're looking in some kind of ambient space, then you also have to take into account, then you have additional contributions which come from the area of the complementary disk. Now what happens is that if you look at the, so the differential then is kind of D0 plus D deformed, where the deformed part is in red. And the problem that you see here is that the deformed part is bigger than the undeformed part, because recall, the bigger the exponent of a t, that means that the norm is e to the minus r. So in other words, this means that if you look at the boundary depth of the differential associated with the undeformed case, and you look at e to the minus its inverse, that's kind of like e to the minus. That's kind of the norm of a right inverse to the differential, and you see that the deformed differential has a norm which is bigger than that, and therefore the deformation is just too big. Therefore, the spectral sequence doesn't converge. So there is so now there's a theorem.
Sorry, I get
Yes.
confused. What is the norm of, like, how do you define the norm of the deformed differential?
So it's just e to the 1 minus r, I guess. No, it's e to the minus 1 minus r. It's just the size of this thing.
Oh, okay.
So this decreases by a certain factor. Like the differential always decreases norms, but like this means it decreases by a small amount, and this, like, since this area is bigger, it decreases by a bigger amount. That's what. Okay. Is that
Yeah.
okay? So the theorem says a certain condition about when the spectral sequence does converge, and the condition may sound a little strange at first, but the key is whether it can be verified. So it says the following thing. It says that there is a certain constant such that if the boundary depth, so if you consider the boundary depth of the domain r times d, so I should have written somewhere where's r times d. So r means, so r is some real number. So when you have a Liouville domain, you can kind of scale. You can scale it down. You can shrink it. So r is some shrink. You shrink the domain by a certain amount. And then I should say that the boundary depth then is kind of linear in this. So this is some way of decreasing the boundary depth by shrinking. So if you've shrunk it enough such that the boundary depth of the intrinsic relative SH, that is relative SH relative to the completion of D itself. If you shrunk it enough so that it's less than this constant, which is fixed ahead of time, and if the locality spectral sequence is known to degenerate on page 1 for this domain, then it means that then it converges. So there's kind of two conditions. One is about kind of the boundary depth being small relative to some fixed constant, and the other is that the spectral sequence degenerates on the first page. And when these two things happen, then we say that then it converges, which means then you have some kind of locality isomorphism. So now you could ask me like when. So first let me pause for questions.
So this condition, like the condition in the theorem, is intrinsic for D, right? Or
yes. No, there are two parts. This is intrinsic for D.
Okay, yes.
The page 1 is already the deformed. Like page 1 already measures the deformation. So this is intrinsic. Yeah, exactly. So very good. So the intrinsic condition is about boundary depth is pretty easy to verify. So I will just say that that, for example, if you consider a torus, then there is no the boundary depth is 0. So everything, so it's automatic. And in many cases which we care about of singularities of SYZ fibrations, you have this boundary depth condition is easy to satisfy. Basically, it's about some kind of convexity. So boundary depth is, if you consider a convex polygon, then the boundary depth is 0. If you consider some star-shaped polygon, then it's no longer. Then you get some torsion, and then boundary depth is not 0. But we know how to satisfy this. So basically, we need to understand how to think of, like when can we verify this degeneration, which is definitely not an intrinsic condition. So that's definitely something which has to do with the embedding. So we definitely know much less about that. Okay, so I don't have some kind of very clean general result, but I want to say something about this. So one can use this locality spectral sequence to define a real invariant of embeddings. And the real invariant is defined as follows. So the locality spectral sequence I was talking about, it involves, you need to choose a real number lambda in order to get a Z filtration. So the filtration is just, you have to decide like what are the windows you're looking at. You're looking at you take the Floer complex and you look at T to the power of lambda times I of that, right? So something like FP of some version of the Floer complex is just T to the lambda P. So you have some choice like that, and that real number is not canonical. It's just some choice. So you can define an invariant of kind of the triple, where you have D and its kind of primitive and the ambient space, and you look what is the first like what is the smallest lambda for which you will have a non-trivial differential on the first page. So that's a real number that you can definitely define, and so that gives you a number. And if this real number, not a real number, it's a number, it's a number which is R. Of course, it's in R. Union infinity. So if that real number is infinite, then we know that locality holds. Now, of course, it's easy to define real numbers. The question is, is there anything we can say about this function? And the thing is, it behaves.
Excuse me. So this number is infinite. So what it means that D1 vanishes?
Yes, it means that D1 vanishes. D1 vanishes.
So you say the following thing. So D1 vanishes. So this means that you have no deformation, right?
Right.
So you say that if there is no deformation, so then locality holds.
Yes.
So that's the message, right?
Yeah.
Okay, thank you.
Okay. And then the point is that it has a lot of nice properties. This function, it's not some arbitrary function. So I will go over a few of these. So first of all, if you you have your domain and you shrink it, then this constant, this number doesn't change. It depends. So in a sense, it depends only on the skeleton of the domain. And then if you change by an exact form, you change the one form by some exact form, which kind of preserves the Liouville property, so the dual is still outside, then this thing still doesn't change, which means that we can think of this as a neighborhood of kind of 0 in H1 of the domain, and also we can see that it's locally an infimum of linear functions, because like a witness to a non-trivial deformation, in principle, will be given by some Floer trajectory and by the evaluation of this class on that. So this is like a linear function, and we defined an infimum. So an infimum is an infimum over witnesses, and therefore this means that we have an infimum of linear function. So it's a concave function. So knowing that something is concave, that's a pretty strong thing. Though I won't go into it. And then another important thing is that if you have a pair of domains, D1 included into D2, and you somehow know, some angel whispered to you that there's relative SH of the so here, of course, everything is relative to D bar, to the intrinsic. So you know, for the intrinsic model, you understand it well enough to tell that the restriction map from the bigger domain to the smaller domain is an injection. Then you can deduce that the deformation invariant of the like tau of D1 is less than or equal to tau of D2. There's just a moment of thought would show you this, because if this is kind of this has no deformation up to some real number, up to some, then if this already has a deformation, if this has a deformation at some point and this still doesn't, then you would get a contradiction to this injectivity, because right before the deformation it's supposed to be injected. Okay, so I don't know if I have like 3 minutes. So let me first. Are there any questions about what I said up to here? Okay, so I just want to very quickly give kind of a small application of this. So let's consider, like I just want to show how we combine these tools to study a singularity. So let's call an embedding which has this injectivity property, like an SH essential embedding. And now let's consider the case of something called the positive singularity. So we take as our M, we take C3 minus this is kind of a copy of C star squared. So minus some cone like this. And on this space, we have defined a Lagrangian torus fibration. It doesn't matter what is the formula, but the singular values are, you can describe them as, you look at the plane, x3 equals 0, which means this one is 0. And inside that plane, you have a certain graph, and all the singular values lie on this graph. And then one can show that if one considers kind of regular fibers, things which lie here, then they are also contained in a complete cotangent bundle of a torus. However, like I've glossed over something. Like when you remove here, you have to kind of modify the symplectic form. Kind of you have to inflate it near this divisor so that it becomes complete. But once you do that, you can kind of remove the singularities and obtain a complete cotangent bundle of a torus, which tells you that the regular fibers are undeformed, right? So the tau of a regular fiber is infinite. Now I can look at tau of, try to study a neighborhood of a regular singularity. So this would be kind of, not regular, a neighborhood of a generic singularity, because like there's this special singular point, but there are these generic singularities. And I'm telling you that these generic singularities, they can be described as a product of an annulus, symplectic annulus, with a copy of the focus singularity. And for this, everything is well understood. So for example, we know that, first of all, we know this boundary depth condition. So we know that it has boundary depth 0. And we also know that that fibers of restriction from D1 to a neighborhood of a fiber is injective. So the fibers are SH essential. So combining this with the Kunath formula, we can deduce that the restriction from this domain to some fiber here is also injective in the kind of, when you consider it relative to like in the intrinsic setting. So this is and therefore we can deduce from this that since we know that the torus fibers have tau equals to infinity, then these domains also have tau equals to infinity. So which means that, so what is the takeaway? Like if you look at this family, you don't have a complete embedding of T star of kind of the cylinder times D1. You only have an incomplete embedding, but still you can deduce kind of locality by the combination of these results. Okay, I think I've gone over time, so I think this is a good point to stop.
Okay, so thank you very much. So let's thank you. Nice. So questions.
So I have a naive question about something you said way earlier.
Okay.
When you remove those Lagrangian tails and you get,
Yes.
you said so basically you said different decompositions give rise to an automorphism with the symplectic.
Yes.
Homology. Is there anything at all that you could say the other way around? Like if you have a non-trivial automorphism, can you maybe construct an M that recovers?
Yeah, that's like can you construct a symplectic? So you're asking, I think, if you can construct a symplectic manifold out of some diagram. I think that's your question. I mean, there are lots of constructions of symplectic manifolds out of diagrams, but yeah, I don't really know. I mean, it sounds like the question about kind of dual, kind of like this is some kind of discussion which tells you how to construct the mirror. And it sounds like you're asking about the opposite. Like if you're starting with kind of the complex side of the mirror, can you reconstruct the symplectic manifold? And yeah, I don't know.
So, more questions?
Maybe it's a silly one, but is the convergence of the spectral sequence easier when the limit is 0? So for example, when D is displaceable in M?
Again, when the limit is 0, when
you had the spectral sequence that doesn't always converge, and you had the theorem saying that under this condition it does. So I'm asking, is it easier when you know that the limit is 0? So the limit, I think, was the homology of D and M. So for example, if D is displaceable,
if the limit
simplify thing or just the same?
If we know that the limit, I think so, because I think this convergence condition, like when to say that a spectral sequence is not convergent, I think it's some condition on some induced filtration on homology. So if the homology is trivial, then however, I should say another, like this thing that there's a difference between these two theorems. Like the locality theorem, which I have with Umut, is also about torsion in relative SH. But like this, the spectral sequence is specifically about relative SH over the Novikov field. it's kind of, you already kind of discard all torsion at the start. So I don't know, like, so that's something to consider.
Thanks.
Further questions? Well, I want to ask a couple of questions. So first of all, I mean, in this theorem, which you stated, so if you have a complete embedding, so you have a morphism of symplectic cohomologies, right? If you have so can you use it in order to detect some knots, so kind of complete embeddings of two different complete embeddings of one manifold to another?
Can I distinct? Yeah, I think we have some, like at least we have some kind of statements like proving that I think we have some statement like this. We have that different complete embeddings associated with different cluster presentations. I think we can show sometimes that they're not Hamiltonian isotopic. Is that?
Yes, so that's very nice. Yeah.
I think we have some kind of statement like that.
And another question which I have, so you mentioned that this tau function is convex, right? So do you have some applications of convexity? So indeed kind of good.
No, the main application of this, like concavity, like why concavity is a good thing is that if you have a concave function, which is positive, like it's also positive, I forgot to say. So if you have a positive concave function, which is whose domain of definition is the entire real line, then it's constant.
Okay.
So that tells you that torsion, like in a lot of settings of SYZ mirror symmetry, this tau invariant is constant because you can say that you can deform these, you have some kind of completeness about these, you have rays in all kinds of directions. And once you like it would be great to be able to say that tau equals infinity. But there's still a gap going from constant to infinity. But it's kind of progress. If you know that it's constant, then you kind of understand that the deformation respects the grading of Floer homology by it respects grading of orbits by their homology class. So say you have L, and you know that the L is a Lagrangian torus, and you know that this thing is that the tau is constant, then it tells you that if you have a deformation, it really goes between an orbit and another orbit in the same homology class. So that's and maybe you have additional tools to rule that out. For example, if you happen to know that the ambient space is atoroidal and aspherical, then that tells you that it's undeformed. So that's one-way convexity. So that's a concrete application.
Interesting. Thank you. So more questions, comments, or
maybe one comment that this concavity and constantness idea we used with Tunkonog and Viana to address this kind of unabstractedness of SYZ fibers.
Indeed, it's exactly the kind of the same kind of set, like this application, the same setting, except that this refers to kind of relative symplectic homology, and that's about kind of obstructedness in Lagrangian Floer homology. So there's kind of the idea, the philosophy is the same, but the techniques somehow going in are somehow different.
Very interesting. So any further questions? Okay, so then let's thank you again for a fascinating talk.